Hi, and welcome back from the CAOS team at Politecnico di Milano. Today, we are going to talk about agent option pricing. An option is a contract representing a financial agreement between two parties, a grantor and an option holder. The grantor gives the option holder the right to buy or sell an underlying asset at a later date within a predefined time horizon. The agreed fixed price of this transaction is called the strike price. In the future, the asset may increase or decrease its value. In the first case, as the option holder has the right to buy at the agreed price, there is a gain. Otherwise, the holder will not buy the asset as will have a loss. Let's now provide an overview on option pricing. Options can be divided into call or put options and provide, respectively, the right of buying or selling the title at a determined strike within a certain date. We can then divide further the options in European, American, and exotic. The first ones may only be exercised on expiry date. The American one, from the other hand, may be exercised on any trading day, on or before expiration. For what concerns exotic, we will talk about agent options. They are a special type of exotic options, whose payoff is computed by considering the average price of the asset during the entire contract term. These type of options are less volatile than others, however, they require a more complex model for evaluation. In this demo, we will use Curran's approximation algorithm. This algorithm computes the expected option payoff basing on the geometric mean of the prices at relevant averaging points. It is widely used thanks to its precision. However, the approximation algorithm is computationally expensive, and it has revealed to be a good candidate to be ported on hardware accelerators, such as Maxeller dataflow engines. Let's see how to design our agent option pricing application with the CAOS framework. As for the other examples, we start by creating a new project and by defining an archive with the source code and the program description JSON file. Once these files have been selected, we can start with generating the IR. This phase will give us a program static call graph with all the functions that have been identified. By clicking on each function, the framework will provide us with its source code. For the next step, we need to provide a description of the architecture and which architectural template to consider during the design. CAOS will automatically check what kind of framework are suitable to our application. For this example, the Maxeller template is the only suitable one, and a report for each function is given. At this point, we need to provide an input for our profiling phase. We need to define a name, an archive, the command line arguments, and then click on Profile Dataset to start the profiling. The result of this phase is a table, showing for each function the self and total time in percentage. The last line of the table shows the overall external calls, that is, the function that have not been defined within the application. Now that the profiling phase is over, we can move to the partitioning. The partitioning The first thing we may notice is that on the right part of the screen there is a static call graph of function that is possible to partition. In the example, the graph is showing us a dependency among calculation and NCDF function. This means that if I want to implement the function calculation in hardware, then I have to implement function NCDF too. So, let's have the framework to decide the partitioning and click on Run Partitioning. We can see that the CAOS framework decided to implement both functions in hardware, as written in the table. During this phase, the candidate functions to be implemented in hardware are translated in MaxJ code. So now, we can move into the function optimization phase. Here, we have to specify the folder with the code we want to start the optimization process with. Now, we have only one, so we select it and we start the pre-optimization IR generation. This phase is necessary, because in the previous file, the functions were translated in MaxJ code. It is observable how the NDF function is no more identified as a function, as it has been embedded into the calculation one. Furthermore, the CAOS framework created a manager function that is used to manage the cores. The stated code analysis shows for each function the value of each analyzed metric. In the example, multiple metrics are showed, for example the number of I/O operations per cycle, or the frequency and the width of the input. After this analysis, the framework estimates the usage of VRAMs, DSPs, flip-flops, and LUTs. In the example, it is clear that the proposed design does not fit into the FPGA resources, as the VRAM is the only resource below 100%. In fact, if we move into the performance estimation phase, we see that the framework starts a design space exploration, resulting in proposing a tiling optimization. This optimization reduces different values as I/O operation per cycle and outer loop iteration, resulting in an overall reduction of our resources, so that all of them now are below 100%. Now that our design fits the device, we can apply our optimizations to the code and perform the post-optimization IR generation. Again, this phase is necessary, as we modified our code in order to optimize it. In fact, by further investigating the calculation function, we found out that there is a line of code stating that the tiling factor is equal to 10. Now, we have a new folder with the code optimized with implementation choices that have been done so far. We select the code and start the implementation phase by clicking on Run Implementation. After the implementation is completed, we can download an archive that contains the binary resulted from this last phase. This concludes our demo video on Asian option pricing application design on CAOS. If you are more interested in the CAOS framework, do not hesitate to contact us.